Thank you. For once, I don't have to unmute myself. Well, thanks for having me here. I was saying to Adriana, if the conference were to held in Kansas, I would have come as well. This is, of course, nothing against Kansas. Oops, how did it go? Oops. Okay, so I will just give away the punchline. Okay, I want to state these some facts or conclusions about child language learning in fairly familiar machine learning terms, but I'll unpack the differences. So one thing we'll see is that child language learning shows phase transitions. You go through some very discontinuous changes from one point to the other point. And the grammar is actually sometimes a partial function, namely there are input values for which the output is not defined. That has to be a desired outcome of language learning. The second point is that children don't seem to provide a perfect fit or optimal fit for the input data, but provide a good enough fit with the input data. This actually has interesting consequences because it seems that children then have a natural regularization scheme that avoids overfitting while still arriving at fairly systematic generalizations across individuals, across communities, across very different input data. And I will say something about what this natural regularization scheme looks like. Okay, I think the difference between machine learning and language learning by children would be fairly apparent as we go on. So, well, this is one of the things children do. They make interesting errors and sometimes systematic errors, then they get out of it. So these are examples in child English. I died you. I said you know. These are not forms available in input data because these are ungrammatical in adult English. But then children make those mistakes systematically, then they get out of them. Because when they're 10, they're not talking this way. This problem is extremely well studied in language acquisition. So here's a very famous finding in a so-called past tense debate where neural nets figure very prominently. I won't give you the background, but this is American English learning children learning the past tense form of ED. This is one child, Adam. For the about 3 years, he did not make a single mistake on irregular verbs. Whenever he used irregular verbs, he used them perfectly. But then right at the age 2 years and 10 months, as captured in the transcript, he produced things like what that felt like, which is clearly a case of a child going beyond the input because the field is not a form that's available in adult English. And also very interestingly, you can see he was actually producing ED-marked verbs for 3 years. He was saying things like walked and talked, but he wasn't doing so systematically. He was doing so only in about 20 or 30% of the context for which a past tense marking was compulsory. Okay? But as soon as Adam discovered ED, the rate of not only he started making errors, but the rate of a regular tense marking shot up overnight. So this is what I meant by phase transition. The child was not actually generalizing at all. Then at one point, it suddenly started to generalize. So that's a question that I've been obsessed with for a very long time. Okay? The other thing I want to point out is to point out some ecological conditions of language acquisition. This partially overlaps with what Anne was talking about this morning. So one of the things we know now is that children's early vocabulary is actually very small. If you look at the finding on the left, this is from a long time ago, you see that by the age of over a year, maybe this is a more famous finding, the so-called 30 million word gap. You can see by the age of 3, children, this is American English learning children, know about 1,000 words if they're on the high end. If they're on the low end, many fewer. Similar findings have been reported from many other languages. But now let's imagine the linguistic ability of a 3-year-old. It's really astonishing. So in other words, the 3-year-old or 2-year-old must be able to learn a lot about a language on a very small vocabulary. And if you think about this vocabulary, it's going to be highly frequent words that children hear all the time, and probably words that are highly relevant to their lives. So I won't go into the early stage of word learning, which is very slow. I refer you to some of the work by me and my colleagues. And this is very much like what the stage of acquisition that Anne was talking about. The acceleration of vocabulary acquisition was enabled by children learning the syntax, or by which I mean I don't mean just syntax, morphology, syntax. Children are forming abstractions. That's what is really driving much of the word learning process. And the other thing I think is also very clear if you look at the data, but probably not as appreciated, is the degree of variability across individuals. So here are 6 children from the so-called Providence corpus. This is American English, recorded very densely from age of 1 to about 3. So this is a very simple measure of how many words 2 children share in common in their vocabulary, the so-called Descartes similarity. If it's 1, they know exactly the same set of words. If it's 0, they have no shared vocabulary whatsoever. So you can see at 25 words, this is 6 children on average, a pairwise average. You can see there's only about 25% of words are shared across any 2 children. Even at 150 words, the rate of maybe only half of the vocabulary between 2 children are comparable, are the same. Yet at age of 3 or roughly or so, their grammatical capacities are not so different at all. This is again well known, that is that the linguistic sophistication of children is best predicted by vocabulary size rather than any particular item per se. So if you following, you can see there's the hints at a particular kind of a learning function that I would argue is actually threshold-based. And that's really where the phase transition, the discontinuity, and so on will come in. And also, this is very well known. This is the language data is very sparse, follow roughly Zipf's law. And this is about a year of data in Spanish. Okay, this is only the verbal morphology. So you can see there are about, 1,500 verb stems. But many of them are used almost only once. Okay, it's only in a certain, very small number of them, and only in a very small number of verbal inflectional categories that are robustly, tested. Nevertheless, you think about an acquisition of morphology by a 3-year-old learning Spanish. Their agreement morphology, tense morphology, are already very, very good. So they're able to form generalizations with a very small, amount of data, but also, very sparsely distributed, kind of data. That's the kind of learning process we're trying to understand when we try to understand child language acquisition, and see how that's different or the same as machines. Well, this is interesting. Okay, so this is what I meant by language. The grammar is actually sometimes a partial function. Okay, so in American English, there's no past participle for the verb stride. You say I stride, I strode, I have. People don't like it. Okay, and there's many such studies across languages. Virtually every language has gaps. Since I'm in France, I'll give you 2 examples. I mean, I don't know French at all, but these were given by previous researchers in French morphology. Apparently, the verb fry and close in French do not have certain inflected forms in the language. I don't know. Okay, but this is what people say. Believe me on the stride case. So what happens then is that after exposure to the language for your lifetime, when you give a new token like close or fry or stride, you are not obligated to provide an outcome. You're not doing argmax. You're not even doing softmax. You actually refuse to produce anything. That's also an interesting fact about human language. It has generated a lot of interesting theoretical linguistics and language acquisition, but that's one of the goals we must meet if we want to understand how children learn languages. So these are the design specifications, if you will, for language acquisition, how children learn. Very small amount of data, about 30 million words, I think, give and take, should give you most of the grammar that children acquire by the age of maybe 3 or 4. Only positive data. This is also interesting. There's some discussion about the use of indirect negative data, namely using unattested forms as evidence for its absence or ungrammaticality. I think that we have to be very careful. Because this combinatorial space is so large, just something is unattested, it's very difficult to distinguish whether that's impossible or simply occurring at a very low probability that it simply haven't been sampled, right? So I think we should be very, really careful about that. Individual variability that we all understand as just vocabulary acquisition. Of course, everybody's linguistic experience is different. But very importantly, the general uniformity in learning outcomes so we understand each other. At the same time, flexibility that enables individual variation is, of course, critically in the case of language change. when the grammar has to change, not transmitted faithfully from one generation to the other. These are the design specifications for child language acquisition. So I'm just give you a simple example. This is just to give you maybe a flavor of how machine learning research has typically conceived the problem in a way that's a little bit different from children, right? So let's say I give you a hypothetical language English, where two verbs, hit, and set, occur 1,000,000 times. For them, the past tense form does not change. But then you're given a bunch of other verbs that do add ed, but they occur very, very rarely. I'm not pointing to any particular machine learning model, but a typical way for machine learning models to work is to optimize for the predictability of the data. So in this case, you should guess the pattern should be no change, because that gives you almost all the data. Whereas, of course, for humans, I think the intuition would be, there's a lot of evidence for this, is that we don't want to treat this as a probability matching problem. We want to actually say this is really the ED form that applies for a diverse range of words. That's where the rule is going to come in. So type and token, this is, of course, a type-token distinction, which is not always distinguished in many settings of machine learning problems. So what I'm going to tell you is a particular theory of what this regularization function is. It's really based on a very old intuition, you know, maybe not really restricted to language. If you go out there, you find some species of birds on some, you know, island. What do you want to conclude about them? If, you know, if many of them, if the 8 out of 10 of them have some property, you might be inclined to generalize to the 11th and so on. But if only like 3 or 2 out of 10 distinct items share some property, you'd be crazy to go all the way. And you say, I'm going to memorize, you know, those 2 or 3, and then for the rest, I don't know. Okay? This is the insight, I think, shared by, but the crucial question is how many would be counted as many enough, how few would be viewed as few enough. So many people have had this insight, going back to the structural linguists, to early generative grammar, even to connectionists, something known as the critical mass, you know, hypothesis. That really means that everybody seems to know that there's a point where the child has seen enough data, then they should generalize. The particular formulation of this is mine, something I call the tolerance principle. I did this about 20 years ago. At the time, nobody believed it. I probably didn't, you know, believe it either. But now there seems to be better evidence for it. I certainly have convinced more people. The intuition is a simple one. The intuition is that you can either have a bunch of words, let's say, that some of them follow a rule, some don't follow a rule. How do you want to organize them? One way is to make a list. I don't care about the similarities or the shared rules some of them have in common. I'm going to make a simple list. The other way is to say is that to think of the way of rule application as with exceptions as a computer program, if then. So you have to list the exceptions, and then you say, I'm going to apply the rule. So in other words, if you for a word that does follow the rule, you have to wait until all the exceptions are examined. And the proposal here is that the learner is going to pick the organization of the grammar as faster. So you can think if the number of exceptions is way too many, then the rule-following items will have to wait longer on average. So that's the motivation behind this. So you can do some mathematics to prove a theorem, if you will. That's helped by a colleague of mine, Sam Gunman. So this is the intuition. So let's say if you 100 words, you can sort them by a list, rank by frequency. So the rate, the access time is going to be constant. It's going to be flat line. And this is going to be the expected time where as expected time when you have X number of exceptions, so where X is 1 to 100. So what you can see here is you simply set the equation to be identity. You see that these two lines cross. Here's about roughly 21, okay? So in other words, if you have 100 items, if you have more than 21 items that don't follow a rule, you don't generalize. You only generalize if the number of items that do follow the rule is at least 79 or higher. Okay? So this is what is going to give us phase trends. You have to take this at face value, for now. I'll give you some evidence for this, right? So you can see why I didn't quite believe this myself, at least when this work was first done. So on the one hand, you can see if you have 10 items, you can tolerate 4 exceptions. So if 6 out of 10, you should be able to generalize. But if you at 100, you need 79 to generalize. If 1,000, it's even higher. Okay, so this is simply the function of the natural log. That is that the ratio of 1 over the natural log of n decreases quite significantly. What I want to say is that, in fact, it's easier to find a generalization when the vocabulary is small. If you're 10, you can put up with, with 40 exceptions. If you're 100, you're already down to 21. Well, the other point I want to make is that this is a principle, this is a parameter-free model. You're giving a set of items, some of them follow the rule, some don't follow the rule. All I need to do is to know the cardinality of those 2 sets. One is, of course, is a subset of the other. The other thing I want to argue is that this threshold is true. It's probably unregressible from the data. This is what I mean. So let's say you go out there, you take 1,000 languages. Some of them have a productive rule, some have an unproductive rule. Let's say this threshold is true. If you take any arbitrary language for the unproductive processes, by assumption, the number of exceptions would be higher than the threshold. For the productive one, the number of exceptions would be lower than the threshold. But the distance to the threshold could be arbitrary, from language to language, or from the corpus to corpus, right? So I would actually argue this is not a threshold you can actually regress from the data as a matter of principle. So in other words, this is a phase transition I was talking about. So if you have 100 words, as long as the number of, you have 20 words, you look up this function. So if fewer than 6 exceptions, you generalize. If you have more than 6 exceptions, you memorize, and you do not generalize at all. So that's a proposal. And this is important because we seem to have this intuition that majority should give you the rule. This is certainly not the case in language. Right? I'll give you a simple example here. English lexical stress. Ann Cutler and others have shown, a long time ago, English is actually primarily a stress initial language, thanks to its Germanic heritage. But nobody treats English as, I memorize 16% of exceptions, just stress it for a syllable. As we know, English stress is sensitive to part of speech. It's also sensitive to the weight of a syllable for reasons, complicated reasons I won't get into here. So you have words like they permit you to get a permit. Noun-verb, you contrast, they will record a record. This is a change that happened in the history of English, getting back probably in the late 1400s. So as I said, convince a few people. And so this is a work, really work of Katie Schuler, a current colleague when she was a graduate student with Alyssa Newport at Georgetown. So here we did what they really did. They taught children artificial language with 9 nouns. In one condition, 5 of the nouns share an ending. The other 4 are idiosyncratic. In the other condition, 3 words share an ending. The other 6 are idiosyncratic. And so, of course, if you plug in the value of n equals 9, you do 9 divided by the natural log line is 4.2. So the prediction is actually here. In the first condition, children should generalize the majority suffix. In fact, they did so almost categorically. In the second condition, this is really interesting. Certainly not the majority rule. In fact, the most common response is say nothing. Children sit there and say nothing. That, I argue, is very similar to Stride-Strode. That is that if your data does not support a generalization, you do nothing, which, as I've seen in the case of gaps, is really the desired outcome for language learning system. This is also experimental work trying to test this model. This is the work of Émerice Emmond and Rushen Shi from UCAM. This was given at BU last year. It was quite striking. So those were 14-month-old French learning babies, but they were trained on Russian. Okay, because Russian had this word order variation where I don't know Russian, but you can describe it as a movement, but it's not exactly movement. So ABC can be mapped to BAC, namely the first 2 words would swap. So that's rule 1. The other rule is that the second and third word, can swap. So the infants were exposed to ABC, BAC, A, B, C, B, A, C. In one condition, rule 1, they were exposed to the other rule in the other condition. But very interestingly, they were exposed to 16 of such ABCs, unique ABCs. This is Russian. They heard only once. They have no idea what's going on. They don't know. This is purely formal pattern learning. That's why I hesitate to describe this as a Russian or as a trees. This is probably a simple linear pattern they're learning. But what's important is that in the first condition, children were exposed to 16 ABCs, out of which 11 showed this alternation. In the second condition, children were exposed to 16 ABCs, out of which 10 showed this alternation. And the thing is that after training, of course, you're given to a new item either to follow that rule or follow the other rule. So you can see children in the first condition, in the 11 out of 16 condition, show a reliable discrimination between the two patterns, but not in the second one. Okay, I was very grateful because if you run numbers, it's actually 5.77. So I have no idea. So this is actually predicted by this principle. I mean, this sounds like science fiction. I have no idea how this is, how this is actually implemented. I have some, speculations about this if people are interested. But in any case, I'm betting a farm on it, right? So we'll just run this model and see what happens. Okay, so this actually takes us to a much older view of language acquisition. This is really a view of language acquisition that goes to earlier era of generative grammar, probably even very early in the 50s, and was still around in the 1960s, which is really the child is performing some sort of distributional learning that's much more consistent with the hypothesis testing idea of learning. And this is explicit, actually best formulated in terms of Peircean abduction. So here's a quote from Chomsky, right? Having selected a permissible hypothesis, the child can use inductive evidence for corrective action, confirming and disconfirming his choice. Once hypothesis is sufficiently well confirmed, the child knows the language defined by this hypothesis. Consequently, his knowledge extends enormously beyond his experience. Okay, so this is a generalization problem. Well, what I give is no more than a theory of what is sufficiently well confirmed. That is that we're gonna run hypothesis formation and testing using the same principle among the vocabulary that children appear to be getting in a fairly early stage of language acquisition, which is, again, small number of items, fairly high in frequency. So I'll give you a little toy example here instead of showing a full-blown computational implementation. So let's say that the task is really, but also to illustrate that I think this kind of a pattern finding scheme is by no means unique to language, it's probably shared across domains. Right? So here's a little problem. Your job is to learn the mapping between numbers and color. Okay, so some numbers are red, some numbers are blue. So how do you do it? So here's a mechanical procedure, a discovery procedure, if you will. So I'm going to count up the most frequent color. In this case, happened to be red. Okay, so 6 red and 5 are blue. I'm going to hypothesize a rule that maps the color to red. Sorry, the map a number to red. So these are the numbers in red. So what do they have in common? Well, it's not a quiz. Let's say you say odd is going to be supported by red because that seems to be the most salient pattern here. Although you have one exception because 6 is not odd, right? So now you're going to use my tolerance principle to check. You say if 6 out of 11 6 out of 1 is 1 out of 6, is that below the threshold? Yes. So now you have at least a reason to postulate a potential rule that odd numbers are mapped to red. Now you have to check it. You have a hypothesis, now you have to verify it, right? So now you want to go on and test this rule if there's an odd number mapped to red. Now you're looking at a different set of data. You're looking at the odd numbers and including the 11, which is blue. So now you apply the principle. Again, in this case, of course, it happens 1 out of 6 is not enough to disrupt this regularity. So you have the rule that a productive one, namely odd number maps to red, you have to memorize. 11 is an exception because it does go blue. Then, since these words are handled by a productive rule with a tolerable number of exceptions, they're removed from the data, then the search continues. Okay, now you only have those guys left. Again, you check that it's easy to see. You can get a rule that even numbers is going to be mapped to blue, but you have to memorize 6. Okay? So as time goes on, this is really, I think this is, I believe or I conjecture this is how children learn languages. So maybe at this point, if you induce two rules, odd and even rule, now you're exposed to more data. Now you see the even rule doesn't work so good anymore because there's three more even numbers, and they are all mapped to red. So that rule disappears because now it falls below the threshold. So that rule is replaced. And possibly in this case, you can do no more than memorizing them. When you memorize, you're not generalizing. So you're given a new item, you have no idea what to do. You have gaps. This is actually necessary because one of the persistent challenges in language is that linguistic rules are very much structured or conditioned. And this is a well-studied topic, so I won't dwell on this here. So in German, there are 5 suffixes. They cover, none is anywhere near the majority that would be sanctioned by as a global default according to the equation, and nor are the facts so, right? Because these endings, as some of you may know, are sensitive to gender and also to its morphology. In fact, the least frequent suffix s is actually productive, as in the case of a new word in German, iPhone, iPhones. So what we're doing is we have a program that basically implements what I just described. That is, we're going to pick up the most frequent suffix, happen to be in here, then look for productive conditions under which first you identify the most productive hypothesis for n, and then you want to see if the data actually contains productive data generalization to support this rule. So I won't give you the details here. This just came out of a Coxsackie meeting later this summer. So we trained this on a very small sample of words, a random sample of words, for English past tense, but as well as German nouns. We find that this recursive search procedure is extremely quick, as you can imagine, but it's able to find the linguistic rules that are interpretable. Namely, you can discover the sensitivity to gender and phonology on the nouns. And so even though you start out with about 500 German words, which is typical data sample size for 3-year-olds German vocabulary, only actually 15% of them require rote memorization. All the other 85% of the data can be handled productively by sub-rules, if you will. And we also found this model is competitive against a neural model. I can't go into the details here. In fact, you get, for English, you actually get a little bit of a dip as input data goes from small to large, because there is a point where children discover ED rule. Because prior to that point, they're not able to generalize yet, as we saw very earlier. So I don't have time to talk about syntax, but I think the idea is the same. That is that, for instance, how do we know some categories are can freely combine? If you look at all the words in a language, no, you can never find all of them being combined with both categories. That's the sparse data problem. But if you look at the early vocabulary, again, high-frequency ones, you see that time after time, the productive rules, once you evaluate a small but high-frequency vocabulary, almost always are tested fully with the combinatorial possibilities, right? So there's a really advantage to children having a small amount of data, where the vocabulary is small but also resides in a high-frequency range, because the threshold tells you smaller vocabulary making it easier for people to generalize. And I should also say something about recursion, because this is one of the big topics here. So here's CP recursion. On this way of conception of recursive structures, it comes down to really lexical learning. Really, in this case, is really talking about, you have a 2-level embedding matrix and embedded. You don't need to more. If you know if there's enough subset of a big enough subset of the CP taking verbs in the data that are using both positions, that's evidence for children to generalize. So there's a paper we wrote on this at BU last year, but also Katie Schuler and Dao-Xin Li have an artificial language study supporting this idea as well. For at least for adults, and they're currently working on children. So let me wrap up. Well, maybe one more slide, right? is to say that I would think children learn languages at a framework level in a way that's a little bit different from machine learning, right? So let's say if you're a very small child, you have learn 20 words, 10 of them go one way, 10 of them go some other way. You don't have to make a commitment. Certainly the equation won't tell you, you don't make a commitment. But what if you about at 60, 50 and 10? Well, then you learn the rule. And then you learn, you probably don't need my principle. Everyone here will know, like, well, you're gonna generalize A. But then the child learns even more words. Which word they learn is completely, it's uncontrolled, right? So maybe they say that maybe B is a productive rule, where A would be the exceptions. So there's no really external function to approximate. The child simply makes up whatever is able to, given the input sample presented in the environment. I think for machine learning, especially if the threshold is correct, it's really you get a step function. It's like real neurons. You either fire or you don't. And of course, step functions are not differentiable, so that's a little bit different from a lot of tools as we find in machine learning. So what I argue here is that we can talk about I-learning. So the I is, unlike the framework of machine learning, certainly in learnability work, there's some external language or grammar to be acquired. The child has to gradually approximate, to it. That probably is just the wrong metaphor, in my view. So to wrap things up, some of the differences between children and machines. This is a time when I was still doing machine learning in grad school in the mid-90s. Traditional machine learning at the time was really, let's specify a class of functions, and let's see which class of functions are learnable, usually using some sort of cost function. And traditional linguistics has also done taking a similar approach. Let's specify a class of grammars, certainly in the case of principles and parameters. Now the job is to figure out which is the grammar we're talking about. I think the new perspective here is actually a little bit similar to deep learning. That is, that their deep learning is we have an algorithm. We're trying to figure out what is actually learning. So I think in this case, there's some similarity that is that there seems to be an algorithm. If you don't like my equation, try some other equation, right? Seems to be some algorithm. Let's study what is L of A, namely the class of functions that are learnable by this algorithm, rather than worrying about what are the class of functions that are pre-specified for children to learn from. So this raises a lot of interesting questions. How much UG do we still need? I think in many cases we can weaken the assumptions of UG because some of the impossible generalizations that we worried about are simply not going to be even tried by children because the data simply does not support it. I have some interest in the role of formal, this is a completely formal process, and role of language and how this connects with conceptual development. It's got some interest in numbers, recently. Maybe Stan and I can talk about it at some point. Does this work for monkeys? Does it work in other domains? Again, I have a very hard time believing this kind of generalization threshold is unique to language. And where is it in a brain? And also, can we put into some machine learning model as a regularizer? This is essentially a regularizer that avoids overfitting. Because again, gaining an actual irregular verb or losing one is not going to change the status of ED. There's some point, though, as we've seen time and again in the history of languages, sometimes functions, rules can flip overnight as the input composition changes to a significant degree. So these are questions I raise. I certainly welcome input. So maybe the last point is that since we were comparing humans and machines, machines are notorious for needing a lot of data. So we know for humans, small amount of data must be sufficient because we know children get only about 30 million words. It's not a billion words, right? But if I'm right, that may also be necessary because that seems to be providing the optimal condition under which generalization in language can occur. Thank you.
Thank you very much.